Hello, Senior Design students in ECE 496. This is Dr. Vladimir Goncharov bringing you a lecture for Wednesday, October 23. This happens to be my father's birthday. Happy birthday, Tata. That's how you say father in Ukrainian. Happy birthday, Baba, in Chinese. My father is 88 years old today. I'm proud to say that he was a lifelong electrical engineer at Motorola Incorporated, and he's the one who gave me the inspiration to become an electrical engineer myself. Today's lecture is a continuation of reliability theory, improving reliability with redundancy. Example number 2. Assume you have a transmitter, such as a garage door opener or a car lock opener, and the probability of a successful transmission to the receiver is lowercase p. Of course, assume that each transmission is independent of the rest, and this allows us now to do some probability calculations. In order to improve the probability that we are successful at achieving the unlocking process, instead of sending the signal just once, assume that we send it n times successively. Then the probability of a success in opening the lock is 1 minus the probability of failure. The probability of failure is 1 minus p for a single transmission, or 1 minus p to the nth power for n transmissions. So therefore the probability of success is 1 minus p quantity to the nth power. You will note that this is the same formula as we had used for n systems in parallel, each with the same probability p of working. So take for example that p is equal to 1/2, a very low reliability. But if we retransmit the signal 10 times, then the probability of success is 1 minus 1/2 to the 10th power, or 1 minus 1 over 1024, 99.9%. Such a small, easy thing to do, retransmit the signal, and we achieve much higher reliability, from 50% to 99.9%. The next example, and the next few examples actually, deal with digital signals, binary signals, and I will introduce a special gate called the majority gate. This gate has an odd number of inputs, and they are binary, and it has a binary output, call it y. Y is a function of these inputs. The way the gate works is y is equal to 0 if the majority of the k inputs is 0, and 1 when the majority of the k inputs is 1. So it simply measures what symbol am I seeing most of at this odd number of inputs. There will never be a tie because the number of inputs is an odd number. This is a truth table for a 3-input majority gate. So there are 8 possible input states, and let me use my laser pointer here. You'll see that 0 is the output when all 3 inputs are 0. 0 is also the output when 2 out of the 3 inputs are 0, etc. Now let's take and apply this majority gate in a very complicated digital circuit. Let's say that we have a circuit, call it C1, which has k input bits and a single output bit. C1 could have thousands of digital logic gates. The probability that its output is correct is based on the probability that each of the circuits inside is properly working. And let's say that it's less than 100% reliable, giving it probability P of working properly. What we can do is use 3 identical circuits, call them C1, C2, C3. Although they are all identical and assumed to work each with reliability P independently of the rest. We take their outputs, which ideally should be the same, and drive a majority gate that takes the best 2 out of 3 in order to calculate the signal Y. So this system will work even when one of the subsystems has failed, because the other 2 will be the majority. Let's find the probability that the overall system works. As I said, the probability that each of the subsystems works is P. Assume that they are independent. Case 1 is when all 3 work, so the majority gate produces the correct output bit. The probability that all 3 work is P times P times P, or P cubed. A second case is when one of the 3 fails, but the other 2 work properly, so the majority gate will still produce the correct output signal. The probability of 2 out of 3 circuits working is 3 times 1 minus P times P squared. Now the way this was obtained is 2 of the 3 circuits work, 1 has failed. So that's where we get this part of the expression. 1 minus P is a probability of 1 failure. P squared is the probability of 2 successes. But there are 3 different ways that we can get this combination. Circuit 1 could fail, circuit 2 could fail, or circuit 3 could fail. So we add up 3 times this probability value to get the final result. Case 3 is everything else. That is, 2 or more of the 3 circuits do not give a correct output, causing the majority gate to produce a false output. The probability of case 3 is 1 minus the probability of case 1 plus the probability of case 2 quantity. So here it is. This is the probability of incorrect output. But the probability that the overall system works is probability of case 1 plus the probability of case 2. A graph of this as a function of P, and also showing the situation if we had a single system, that's the red line, that works with probability P, shows us that if the reliability of the system is greater than 50%, then we are guaranteed an improvement with the majority gate circuit. If the reliability is equal to 50%, they operate the same. This is an interesting situation, because for binary output, if you have 50% reliability, it means you're flipping a coin. It means that 50% of the time it's correct, 50% of the time it's incorrect. You might as well be flipping a coin. For 0% reliability, that means that 0% of the time you're getting the correct answer, or 100% of the time you're getting the wrong answer. Well, you know, we can put an inverter after that and we would get the same as a 100% reliable gate. So these are some of the interesting statements we can make But concentrating in the range 0.5 to 1, we see that the majority gate circuit improves performance, at the cost of more circuitry, of course. For example, when the probability that one system works correctly is 90%, this majority triple redundancy circuit gives us a reliability of 97.2%. Of course, we can increase this even more by adding more subsystems. Has to be an odd number, so 5, 7, 9, etc. With 5, for the same reliability as my previous calculation, we now get 99.14% reliability of the overall system. The next example again deals with digital logic, and we are given a goal. Using only 2 input AND gates, 2 input OR gates, or 1 input NOT gates, which are called inverters, design a digital logic function having a NAND input-output characteristic. Well, this is easy. Put a NOT gate following an AND gate. That's called a NAND. But we are given some extra information to take into account. Assume that the AND gates and the OR gates are fairly reliable. They work with probability P sub A for the AND gates. There's only one failure in every 100,000. And the OR gates fail 1 in 50,000, so their probability of working is 1 minus that. But the inverter is low reliability compared to the others. It fails once every 200. So it's like pulling parts from a parts bin, and you're told that 1 out of every 200 inverters will be faulty, but you have no way of knowing that in advance. The AND and the OR gates are much higher reliability. Now, using these reliability values, let's see what the reliability of our original circuit. It is the probability that the AND gate works correctly times the probability that the inverter works correctly. And I've expressed this in the form 1 minus the probability that it fails. And you see that a probability that it fails is not really set by the AND gate. It's the weak link is the inverter. It works with probability 1 over 200. I should say it fails with probability 1 over 200. So taking into the account that the AND gate can also fail, this has lowered our reliability slightly, but pretty much close to that of the inverter. Let's design a NAND circuit having much, much higher reliability. And here's how I propose to do it. Let's take 3 of our original circuits and put them into a majority gate. That way, if one of them doesn't work, the other 2 will be the majority. And hopefully this will improve overall performance. The problem is, we also have to build a majority gate using logic gates. And those logic gates include ANDs and ORs and perhaps inverters. Let's take a look. This is the truth table for a majority gate. If you express Z in terms of, you get the upper expression, but that may be simplified to the lower expression by combining terms and purposely avoiding inverters, because we know that inverters are the lowest reliability component. This way we can have a high reliability majority gate. No inverters are needed. That's a big plus. In fact, this is kind of a unrealistic scenario, because inverters are usually much more reliable than the more complicated OR and AND gates. But for the sake of this example, assume these statistics to be true. Here is the logic circuit using only 2 input gates as we were given for the majority gate. It implements the function z equals a and b, or b and c, or a and c. So it requires 5 gates, 3 and 2 or. And the probability that it works is based on the probability that each of those 5 gates works. So 3 AND gates, p sub a cubed, 2 OR gates times p sub o squared equals a probability that the majority gate works, and that is 1 minus the failure rate, 1 in every 14,000 or so. So it's got a high reliability compared to the NOT gate. The majority gate will give the correct output when all the NAND gates are working, or when at most one of them has failed, assuming that the majority gate also works. So we have to factor in the probability that the majority gate is working. I've come up with this truth table. A, B, and C at the top are the outputs of the NAND gates. And anytime I'm asking the question, is A equal to X, Y not, I'm simply asking, is that NAND gate working or not? Now, we can tolerate a no in a given row, but we cannot tolerate more than one no. So towards the bottom, you see all those no's appearing for the Z. The majority gate starts producing the wrong output. I've calculated the probabilities for all of these, and what we want to do is calculate what is the probability that the majority gate will be producing the right output, assuming that it works perfectly, of course. And that will be the sum of the probabilities of the first 3 rows plus the 5th row. And that would be this sum, but then you multiply the whole thing by the probability that the majority gate works. It is independent of those. And use the value that I came up with previously. You'll get now the overall reliability of this circuit, which is 1 minus 1 over 7,000 or so. So that means that it fails once out of 7,000, approximately, as compared to once every 200 that we had for the original circuit. So we have gotten an improvement. Here's a different approach. Let's overcome the low reliability inverter by first designing what I will call a super inverter. It will use a majority gate to give us the correct inverted signal W naught. V is equal to W naught with probability that the 3 inverters have 2 or more of them working. And we see that the majority gate gives us a much lower failure rate than we had for the single inverter. Instead of 1 out of 200 failures, it now gives us 1 out of 7,000 failures or so, 6908. So we'll call it the probability that the superinverter P sub Si works. Now when we put that following the AND gate, we get an overall reliability of 1 minus 1 over 6070, which is not as good as what we had previously using the majority gate. But that's because the AND gates were not included in the redundancy, just the inverters. But the results are comparable. Finally, consider this. Have 3 NAND gates, this time made from superinverters, so each of those circuits has its own majority gate. And then take those outputs A, B, C and feed them into yet another majority gate. This has got to be the best one so far. And yes, indeed, it gives us a failure rate of only 1 over 14,270, which is excellent compared to the original failure rate for the simple circuit, which was 1 out of 200. At a price, the price we pay, instead of one AND gate and 3 inverters, we now have, one AND gate, 1 inverter, we now have 3 inverters, 15 AND gates, and 8 OR gates, when taking account all the majority gates that we needed to use. So, this is the price we pay for improved reliability. The next example deals with transmitting binary code words and having an extra bit in order to help us detect if a bit error had occurred. This bit is called a parity bit. Assume that we have a packet of bits that we'd like to transmit. It's a 7-bit binary code word having 2 to the 7th possible states or permutations, or 128 possible code words. Assume that each bit is transmitted separately, such as down the serial communication channel, one right after the other, and that the probability that each is correctly received is p, independent of the rest. The probability of receiving the entire code word correctly, if any one bit is received with 99% reliability, is then p to the 7th power, because there are 7 bits, or 93.2%. Furthermore, if there are any errors, we don't know about them. They go undetected. By adding a parity bit, this one with the arrow pointing to it, B8, we can now detect if a transmission error had occurred. Here's how that works. B8 is a function of the other bits. It is the exclusive OR. Another way of looking at the exclusive OR operations here is to say it is the least significant bit of the sum in binary of bits B1 through B7. This scheme is called even parity because when B8 is calculated this way, it turns out that the total number of ones in this 8-bit code word now, including the parity bit, will now be an even number. Total number of ones will be even. You can also use odd parity, it doesn't matter. So, what we do at the receiver is we wait for the 8 bits to come across the communication channel, and then we recalculate B8 based on the first 7 bits and see if our recalculated version matches the one that we received. If it doesn't match, then we know that 1 or more bit errors had occurred, but only odd numbers are detected this way. Even number of bit errors go undetected. And remember, one possible error that may occur is that only the parity bit is incorrectly transmitted. All the rest may be good. So, if our calculated parity and the received parity bits do not match, what's the probability of that happening? Well, there could be one error out of the 8 bits, and there are 8 possible ways that can happen. That's the first term. There could be 3 errors and 56 different ways that can happen. There could be 5 errors, also 56 ways, or there can be 7 errors. Odd number of bits could be incorrectly received. 1, 3, 5, 7. So for example, with the single bit probability of correct reception being 99%, the probability that we will calculate some problem, that our calculated parity does not match the received parity bits will be 7.46% probability. So this means that we are concluding that something is wrong with the transmission 7.5% of the time, and we can request, if we have two-way communication, we can request a retransmission of that packet. So that's something that can give us much, much higher reliability then. With that error rate, the correct parity is calculated with probability 92.54%. Now, I mentioned previously that it's possible that only the parity bit is incorrectly received. That happens 0.93% of the time. So out of the previously calculated 7.46% error detected, 0.93 of that is due to the parity bit only being incorrect, but not the data bits. Of course, we don't know which of the bits is incorrect, so we would ask for a retransmission anyway. Now, if there are an even number of bits incorrectly received, they will go undetected because the checksum, as it's called, will match the parity bit. And here I've calculated the number of ways that can happen. If there are 2-bit errors, there are 28 different ways that 2 out of 8 can be in error, 70 different ways that 4 out of 8 can be in error, and 28 different ways that 6 out of 8 can be in error. And then the probabilities of those happening. So, for example, with p equals 99%, the probability that a bit error occurred, but it had not been detected, is only 0.26%. Here's an interesting way of looking at our results. Across the columns, I've written negative result, positive result. This refers to whether or not the checksum is equal to the parity bit that we received. And if they are the same, I call that a positive result. No error detected. It may not be true that our received code word has no errors, but at least our parity bit tells us that. A negative result is when the parity bit tells us that an error had occurred. Along the rows, I've labeled one or more data bits are in error, and notice I've underlined data because I'm not including the parity bit error as an error in the data bits. Or there could be no data bits in error. So the way to get a false negative, for example, we detect an error because the checksum does not match the parity bit, but there were no data bits in error, only the parity bit was received in error. Now I've added some probabilities to these columns and these rows. These are derived from the equations, from the formulas that were presented in the previous slides. You see that the probability of the first column occurring is 7.46%, so 100% minus that is the probability of the second column occurring. A positive result. That means the checksum matches the parity bit at the receiver. Likewise, along the rows, the probability that there was actually an error in the data bits, the way we receive them, is close to 7%, or error-free reception of only the data bits is close to 93%. there are now categories called true positive, true negative, false negative. This refers to the categories as you see here, and we're very interested in reducing the false positive. Because if we receive a signal telling us that something's wrong, but nothing is actually wrong, that's a false negative, we can usually ask for a retransmission of the entire data word by the transmitter. But in the false positive, we have no clue that an error had occurred. Of course, true negative and true positive are good results. So here are the calculations, and I've put in bold the one that we worry about the most. It's quite low, only 0.26%. The others, true positive and true negative, are what we want to have. Although we'd like to have true negative as low as possible as well, because this is wasted transmission. We have to ask for a retransmission if we detect that something is wrong. A false negative, close to 1% of the time, only the parity bit is incorrect, so we ask for a retransmission for no reason. Now let's go to our final example of this lecture. And now we'll look at detecting and correcting bit errors. So not only can we detect a bit error in a transmitted binary code word, but also correct simple bit errors. The specific code that I will use as an example is the Hamming 7.4 code. In this code, there are 7 bits total. 4 of them are data bits, and 3 of the 7 are parity bits. So now we have special bits allocated for the purpose of not only detecting errors, but also correcting some of them. To get an idea of how this works, let's define a Hamming distance between two code words as the total number of bits in corresponding positions that differ in the two code words. For example, the Hamming distance between these two code words is 1, because only 1 bit is different. Here, the Hamming distance is 3. All 3 bits are different. Here, we have 2, because the last 2 bits are different. And here, the Hamming distance between the two code words is 0. Now that you've gotten the hang of that, let's apply that to the Hamming code. What we want to do is to transmit only code words that differ from one another by at least 3 bits. That means the Hamming distance between any code word and the closest other code word is 3. There might be some that are at a greater distance than 3. But no code words differ in just 1 bit. So that means if we have 1 bit error, we will not mistake it for another code word. This way, a single bit error can be detected and corrected because since the nearest code word to any other code word is 3 bits away, 1 bit being an error makes it easy to discover which valid code word is closest to that. And there will only be 1. Therefore, we can replace the incorrectly received code word with the correct valid code word. If 2-bit errors occur, this will be detected as an invalid code word, but by selecting the nearest code word to that, we will now choose the wrong code word. So therefore, the error is not corrected. We will receive an incorrect result. And 3-bit errors cannot be detected because it appears to be a correct code word. So we cannot detect it, therefore we cannot correct it. But of course, 3-bit errors are much less likely to occur than 2-bit errors, and they are themselves much less likely to occur than a single-bit error. So we hope that most of the time we'll be able to have a single-bit error that is detected and corrected. Here's an example of a transmitted code word that had the first 4 bits equal to 1 and the last 3 equal to 0. At the receiver, the first bit of that string was incorrectly received. I put that in red. That's a 0. Notice that it has Hamming distance 1 from the original valid transmitted code word. What we received, therefore, may be compared to all the valid code words, and the nearest one to it, the one that was transmitted, will be selected as being that which we suppose had been actually transmitted. The nearest other code word to this is distance 2 away, and I show that below. If you have a 7/4 Hamming code, there will be 16 different code words. These code words are at a distance of 3 or more from each other. I came up with this list by writing a small computer program where I generated all possible permutations of 7 bits. So originally there were 128 rows in this matrix. Then I started at the top row, compared it to all the other rows, and eliminated the rows below it that were at distance less than 3. And I then dropped down to the second row and did the same thing, eliminating all the code words below it that were closer to it than distance 3. So these stay in the correct order as far as binary value, going from all zeros to all ones. But all those that were skipped were not acceptable Hamming code words. If you highlight the first 3 rows and then the 5th row, ignoring all the remaining rows that are not highlighted here, you will see that you have 4-bit code words, counting from 4 zeros all the way up to 4 ones, covering all possible permutations of 4 bits. These are the data bits. So if you have data bits 0, 0, 0, 0, then to form a Hamming code word, you include 3 extra bits that are also 3 zeros, etc. Now, the theory gives precise ways of generating the extra parity bits. They are exclusive OR combinations of other bits. And I've skipped that part in this discussion because I think it's just an unnecessary complicating feature. The important thing to realize is that we have 3 bits of overhead that are added in order to do error detection and correction for single bit errors when we have 4 data bits. Now that means that when you transmit a 7-bit Hamming code word, you're only transmitting 4 bits of data. So you can say that it's got an efficiency of 4 divided by 7 times 100%, if that's what you want to call efficiency. I'll call that efficiency. The way that Hamming codes work, the number of bits that form a code word are always chosen to be 2 to the r minus 1, where r is an integer. So in the previous example, we had 7 bits. That would be for r equals 3. Then of these, there will be r parity bits and k, which is n minus r data bits. The Hamming code word design process is one that guarantees that the nearest distance between any two code words is 3. And that allows us to correct for single bit errors. Such a code is called a Hamming n, k code. So using my definition of efficiency of the code, that is the fraction of total that actually conveys data, turns out that the Hamming code has an efficiency that may be calculated as a function of r, where r is the number of parity bits that are included. This, by the way, is maximum efficiency because it assumes that we're using a total number of bits that is 2 to the r minus 1. And we may be using fewer bits than that. That is, not taking full advantage of transmitting all the data bits possible. I've calculated the efficiencies of different Hamming codes. The first row is the Hamming 7,4 code. So essentially 4/7 is 57%. And it's interesting to note that the efficiency grows rapidly as r increases. You can have n equals 63, a 63-bit code word, of which only 6 bits are extra. Those are the parity bits, giving 57 data bits and 6 parity bits for a total of 63 bits. And that is 90% data and only 10% parity bits. Okay, well, that's about it for this lecture. Thank you for your attention. There will be no homework from this lecture.